Hello guys, welcome to this video. In this video I want to talk about how you can convert a Neumann Gefell MV691 microphone to 48 volts phantom power. Now this is the microphone that I'm talking about. They are quite familiar and there's a few of them around and you can easily find them here in Germany at least. And they are still very sought after in recording studios and also for amateur recording people because they have a very nice sound and also they are a very good value for the money. There's one problem. Originally they were equipped with a PSU and you would use this 12.6 volts PSU to power the microphone. It's a totally proprietary powering scheme and it makes things much more complicated because you need more cables, you need the PSU, and so I think it's really worthwhile to convert this microphone to phantom powering 48 volts so you can use it with regular recording equipment, mixes and all that stuff, whatever you like. If this sounds interesting to you, stay tuned and come a little closer. On my table I have already placed a bunch of these microphones. They are not all of the type MV691 like this one, but they all share some similarities in their circuit design and also exterior design. So I want to talk a little bit about this. This is actually a family of microphones that was produced by Neumann Gefell in the late 60s, 70s, until the 80s. With very slight modifications, and they all share some similarities, as I said. So you will find a 7-pin Tuchel connector on all of these microphones. This is a norm which is not used any longer, and in the 70s there were quite a few microphone companies using their own standards until XLR connectors became a standard that is now used by pretty much all microphone producers. So this is not an MV691 but an MV692. You can recognize this type by the two switches. It has a pad, I guess a 10 dB pad, and it has also a low cut filter, so you can filter a little bit of noise if you have problems with low frequency noise when recording something, or on stage. It's quite common on stages that there's a bit of low frequency noise. Then this microphone is intended to be used on stages. It is the exact same circuit like the MV691 that I have here, and that this is the one that I want to convert. This one and this one are already converted to 48 volt phantom powering. And this one has a slight difference here at the capsule head. The capsule itself is the exact same capsule like here, only it is mounted with a suspension, so you can use it with a microphone stand on stage, and other than that the circuit is exactly the same. Now one very nice option if you have those microphones and you are not able to do the modification yourself, the modification to 48 volt phantom power, you can also send it to the company that made those microphones. They are still around. Their name today is Gefell, and they can do the conversion. As you can see, this is a very high quality job. What they do, they also renew the painting of the tube, and what is very convenient, they also exchange the socket, so you get an XLR connector instead of this old Tuchel connector. So here you can see it's now time to move the cable in a little bit. If you modify such a microphone, you can simply keep the old Tuchel connector on the microphone end and then install a regular 3-pin XLR plug to the microphone, and then you'll have your audio connection. Of course, you can only do this if the microphone is internally converted to 48-volt phantom powering. Otherwise, the microphone could be destroyed or at least damaged. So another way of converting these microphones or using them with modern recording equipment is, of course, if you have only this type of microphone, you could then, of course, also modify your preamplifier that it does not use 48 volts phantom powering, but 12 volts phantom powering. Originally, these microphones were equipped with phantom powering of 12 volts, as well as using the fourth pin on this 7-pin XLR, not XLR, on 7-pin Tuchel connector. So you can feed it in two different ways. 12-volt phantom powering is possible, but I would not recommend doing it this way, because should someone else use your microphone and they don't know that, or just because the cable fits to a modern connector, you can only use a modified recording amplifier or a modified mixer. Yeah, just because the connector fits does not mean that you can operate the microphone on any recording amplifier or any mixer. You need a modified mixer recording amplifier. So I would recommend you do the internal conversion if you want to operate this microphone safely with this converted plug as well. Now let's have a look at the schematic of the microphone so we can see what needs to be done. Here on my screen you can see the schematics for the MV692. It's the 12-volt version, as it says here. The microphone that I want to convert to 48-volt phantom powering is not a 692, it's a 691. The schematic is very similar. The 692 has this IC here as an amplifier stage, whereas the 691 has a regular transistor amplifier stage. And also the 691 does not have these switches, the low cut and also the pad. So other than that, these microphones are pretty much identical, and especially the powering scheme is identical. So we can use this schematic to explain what is going on. Now, as you can see here, originally the microphone uses 4 pins in the connector. So obviously these 2 pins are the audio signal, 1 and 2, it's the secondary of the audio transformer. And then from the center tap of the transformer, you can take whatever voltage is present there to power the microphone. And originally the microphone was designed to be used with 12.6 volts. Now, it seems a little bit odd when everyone uses 48-volt phantom powering these days. Why would they use 12-volt? Actually, there is quite a few norms for phantom powering, and one is called P12, then there's also P24, and then there's P48. So there has been a norm for phantom powering of 12 volts and also phantom powering of 24 volts. And sometimes what happens is people invent norms, and then a little bit later the market decides what they want to use and what they find most useful. I can only speculate. At the time when the microphone was invented, most mixing desks were not equipped with phantom powering. It's a more recent invention to have phantom powering at the mixer. So when people used tube microphones, they were used to using their own PSUs, so they were probably perfectly fine to use a PSU for a transistor microphone as well. And only a little bit later they figured out it would be less hassle if you would not need a PSU for your transistor microphone and have a standard to power the microphone from the mixer or recording amplifier. Now here you can see probably why the 12-volt phantom powering was not widely adopted, because in a condenser microphone like this one, a real condenser, not an electric condenser, you always need power, a static voltage for the microphone capsule to charge the condenser, which the capsule is. And you have to build some sort of converter. This is what they did here with this section. In order to produce a capsule voltage in this microphone, the capsule voltage is around 60 volts. And if you have a very low supply voltage like 12 volts, this would not be enough to have a good capsule voltage. So you always need the converter. And if you use 48-volt phantom power, which was adapted much later, then you can directly use 48-volt phantom powering to produce the capsule voltage. This is my speculation why P12 and also P24 as a norm were not commonly used. However, many people don't know that the Gefell MV691 and 692 were originally designed for phantom powering, but not for phantom power of 48 volt but 12 volt. So what we can do is open the circuit here at this point, because if we apply a phantom power of 12, I mean not 12 volt, I mean 48 volt here at these pins, then we have 48 volt at the center tap of the transformer. So we have to remove these two components. These two diodes, they only protect the microphone from having a reverse voltage going in. So as I said, you can also use this proprietary fourth pin. This is how they did with the original PSU. So they would feed the power via this fourth pin. So we will need to remove these components, and this diode together with this diode is inside of one single package. It looks like a transistor, but it actually is a double diode. You can also see that it's called D1/2 and here it is called D2/2. So it's one and the same package. And then we have to insert some sort of voltage regulator here. Now I have seen some circuits where they only put in a resistor here, and of course you can drop the voltage with the resistor. There is just one problem. If your mixing desk does not produce exactly 48 volt phantom power, but a little more, then you will not drop enough voltage here with the resistor. And if it produces less than 48 volts voltage, you will drop too much here with the resistor, and the microphone in both cases will be either overpowered or underpowered. So I think the best solution is to build an active regulation circuit here. There's one problem. There is not a lot of space. As you have seen, it's just a regular microphone tube, microphone body, and everything needs to fit in. Okay, let's look at the regulator circuit. Here you can see a regulator circuit, and this is also, probably you recognize this section, an original Gefell schematic. So it seems they have also produced a variant of this microphone which used 48 volts phantom powering to begin with. Now I have never seen one that was originally equipped with this circuit. I only know the ones that use the proprietary connectors and also the proprietary powering with 12.6 volts. However, you can see this is a simple shunt regulator circuit which uses a Zener diode, two resistors, and then this electrolytic capacitor to regulate a voltage. And with 12, when you compare it to the other circuit which only used one diode here, we know that the internal voltage of the microphone is a little less than 12 volts. So the original power supply had 12.6 volts, and then you drop a little bit of voltage with this diode that was installed here at the center tap. So the internal voltage will probably be something around 11.8, 11.9 volts. So we have to select a matching Zener diode here to get almost 11.8, something like this. 11.6, 11.7, 11.8 would be fine. So that's the circuit that we have to build. And I'm using SMD components because there is not much space in the microphone body. So here on my bench you can see this little voltage regulator module that I have already shown you in circuit. Pardon the camera movement, I'm holding the camera with my hands, otherwise it would be impossible for me to film it. The board is so small. I will place a €1 coin next to it so you have a comparison, and maybe an alligator clip so you can see this is really a tiny board. But this is the space that I have inside of the microphone, and of course I have to use the space that I have, and I cannot use more space than I have. So you can see this is the way I like to set up these little voltage regulator boards that go inside of the Neumann Gefell MV691 microphone. I basically use this perf board, and I also like to use this double-sided perf board because these holes, they are contacted through. So this gives you the opportunity to solder all the components to the top side, and when you cannot make connections by connecting components directly together, you can then use the underside and make connections with tiny wires on the underside, and this gives you really a lot of opportunities. Now you can see I used a standard transistor. This is an East German transistor. The type is SF829D. That's standard transistor. It can handle collector-emitter voltage of 80 volts. Now I like to use components where I don't have to come close to the maximum ratings. I always have components that will only use a partial amount of the maximum rating. So I keep everything safe, and yeah, that's the way I like to do. Then you can of course see the condenser, the electrolytic condenser. Then here you can see on the side 1 and 2 here, these are the two resistors, and then next to the two resistors, it's probably very hard to see, here is the Zener diode, and that's basically it. And then you have 3 wires. The orange wire, this is where the voltage comes in. Then you have the yellow wire, this is where the voltage goes out, and then you have a ground wire. Maybe you can see that I already have connected I already have connected a meter here, and I also have connected the power supply, and I now want to switch everything on so we can check how this little module works. Here is where I connect to the ground of my PSU. This wire, the white wire, goes to the terminal of the meter, so I can measure it. And here I have connected on this wire, the red alligator clip, I have connected the PSU, and on the yellow wire I have another red wire that goes again to the meter, so we can see what's going on. So I will now switch on the PSU so we can see what's going on here. Now this meter here does not show really exact values, but it's close to what is really happening. So yeah, maybe we trust this meter a little more. We have about 2 volts now coming out. Now, just like with any other voltage regulator, it can only regulate if you put in excess voltage. So we want to regulate 12 volts. So we have to put in more than 12 volts, and we have to see if the meter stops at around 11.6, 11.5, something like this. So what do we have? 2.93 volts, 3.3 coming out of the module, going up. Now close to 5 coming out, and a little more, 7, 8, 9 coming out of the module, 11.2, 10.8 coming out. As I said, this scale is not quite correct. It's more like an indicator. It's not a correct meter. I always use my regular meter when I check the voltages. Now you're seeing the effect. I'm at 12.8, but I'm getting 11.6 out of the regulator. Let's go up more. I'm at 15.9, 11.6 output. Now 19, let's go to 20, 11.6 at the output. And let's go even higher. 38 volts, 11.6 at the output. And let's go at the end of the scale, we have 38.6. This is all I can get from the PSU. And we get 11.6 at the output. So the module works perfectly well. In the microphone, it will have to handle a little higher voltages than we had here. Here we stopped at 38.7, and in the microphone it will be 48 volts phantom power. Now the module is ready to go inside of the microphone. We have built the module, we have tested the module, and we can now install it. On my bench you can see the microphone. I have opened it and I have already desoldered the components that I have to remove in order to install the new voltage regulator. As you can see, here is the 3 pins for the double diode. It looks like a transistor. In fact, it's a double diode. We don't need it anymore. And here is the space where the condenser was soldered in. So now the microphone is ready for the new module to be installed, and I have to isolate the module because there's some components underneath, and I will basically place the module above here and then wire the connections, and then the microphone should work. If you have to do some troubleshooting with these microphones, here's some hints how you can do this. As you have seen on the schematic, the microphone was intended to be used with a 12.6 PSU. And of course, 12.6 volts is not enough to have some static voltage for your microphone capsule that screws onto here. So the capsule voltage is 60 volts for these microphones. And you have to find a way how to generate the capsule voltage. In this microphone, they used a converter. And this is the circuit. Now, these days, you would probably find highly integrated components. You have boost converters readily available. But in the days back then, they used a transistor circuit. This is the transistor, that is a switching transistor, and then a coil. And then here is the rectifier, and you will get the capsule voltage here on these 2 diodes. So the first thing that you can do is check if there is voltage on the diode, on the 2 diodes. Of course, you have to feed some power to the microphone via the plug. And then the transverter, as it is called, should work. And you have some almost 50 volts on the diodes. And this voltage gets filtered a little bit, and you know, there's some resistors, so the voltage will drop, and at the capsule you have 60 volts. So what I do, I separate the schematic into the two parts of the microphone. The schematic is, one part is the signal path. So you follow the signal in the signal path. So this is the first transistor, which is right at the beginning here. This is this one. That's a FET. So here you can probe the signal right at the gate of the FET. And if you have voltage coming, then you should be able to see the signal at the gate of this FET. And then you can easily use the two resistors here. This is the source resistor, this is the drain resistor. This one is the drain resistor. I'm sorry, got that confused. And you can probe here. You would also see the signal. And then this transistor is used as an amplifier here. When I put my probe on this transistor, the circuit started to oscillate, but you can use the transformer. I have to rotate the microphone. Here are the transformer tabs here, and you can probe the signal here. So basically you have to get one signal coming through the whole microphone in order to have a working microphone. This is how you troubleshoot it in case there should be something wrong. Fortunately, this one works perfectly fine, and I don't have to change anything else except installing the voltage regulator. The voltage regulator module is now installed inside of the microphone. I have made these two soldering joints new. This is where the voltage comes in from the center tab of the transformer. And here we enter the microphone circuit after the voltage regulator. Also here you can see the ground connection. I'm using an existing ground connection where the board for the microphone will connect to the chassis. Okay, let's have a look at the other side. You can see that I have already placed a little bit of tape above the electrolytic capacitors that are under this little board here, and I have just enough space to fit this in. I will now add a little more of insulation, and then I think I'm about ready to test the microphone, and we will see you there again. So the module is installed inside of the microphone. As you can see, I have completely isolated the small module, and it fits in here really nicely. So the tube will also fit on with no problems at all. Now the only thing left that I have to do is to check the microphone with the 48 volt phantom power, and I will use my mixer again. I have installed the capsule, and the previously existing original microphone cable can now be used with a normal XLR plug. You can install a normal XLR plug. This goes to the mixer. So, what do you think? Will we get a signal? So I will have to move the microphone to here so you can see it, and I'm tapping on the capsule, and we're getting a signal. Also, I have to say I have headphones on, and I can hear that we have a perfectly fine signal. There's a little bit of hum on it, which is perfectly normal because the tube, the shielding is missing. So the only thing left to do is to reassemble the microphone, and then maybe we should try it out with my guitar. See you there. So guys, this is it, and thanks for watching. I hope you enjoyed this video as much as I enjoyed making it. At the end, I want to say a few words of caution. I leave it to your own judgment whether you should do a conversion like I have shown in this video yourself, or if you should rather ask another technician to do this or even send it to the factory. It is important to understand that this is not a beginner's DIY project. It requires a lot of skill. You have to be able to make very clean solder joints. You have to be able to work with very small components. You need to be able to work with schematics and all that stuff. So if you want to use this video as entertainment, I know that some people will watch videos like this for entertainment purposes, which is perfectly fine. But if you intend to do a conversion for yourself, I leave it up to your own judgment whether you should do this, or maybe even send the microphone to the original factory, or have more experienced technician do the work for you. It is important to understand that these microphones are very sensitive devices, much more sensitive than, let's say, an old radio, which is much more rugged and you cannot easily destroy something. So I hope to see you next time. Please come back anytime. There will be more videos like this. Bye for now.